we're going to have a 50-minute talk, and then we'll roughly have about 10 minutes for questions, and that will all be recorded. And then we will turn off the recording, and we can move to a more sort of general discussion afterwards, and that won't be recorded, so you can ask any of your more controversial questions then. Importantly, if you're joining on Meet, please make sure you're muted so we can hear the speaker. If you have any questions, please put them in the chat in the first instance, and we will pass them on to the speaker at an appropriate time. And that also applies if you're watching on YouTube, because we'll be checking the chat there as well. I think that's everything. Over to you, Matteo, to introduce the speaker.
Thanks. It is my pleasure today to introduce our speaker, who is Tengyan Xie. Tengyan is a PhD student in computer science at the University of Illinois at Urbana-Champaign, working with Nan Jiang. Before that, he obtained a master in computer science at the University of Massachusetts at Amherst. Prior to that, he obtained a bachelor degree in physics from the University of Science and Technology of China. Tengyan research focuses on reinforcement learning, contextual bandit, and causal inference. In particular, he has recently focused on exploration in RL and batch RL. And today's talk will indeed focus on batch RL. And in his talk, we will learn more about the use of pessimism for efficient offline learning. And with this, the floor is yours.
So thank you so much for having me here. So let me start. My name is Tengyan Xie. So today I'm gonna tell you about our recent work, Bellman-consistent Pessimism for offline reinforcement learning. This is a joint work with my advisor Nan Jiang, as well as Ching-An Cheng, Mineiro from Microsoft Research, and Alekh Agarwal from Google Research. Oops. Yeah. So at first, let me set up the problem that we are concerned with in this talk. So I think everyone here is familiar with the problem of reinforcement learning, where we are trying to learn a policy pi that maximize the cumulative reward, and we will call it J of pi later. So in our today's talk, we mainly focus on the offline reinforcement learning, where we only have access to the offline data and no interaction with the environment is allowed. And I should emphasize that the main goal of our work is to provide a theoretical framework that works without assuming any coverage assumptions on data, whereas most of the existing work usually assume the data is exploratory enough. So before diving into the detail of our proposed approach, let me introduce some key notations and basics I will use in this talk. So we study the infinite horizon MDPs, and we use gamma to be the discount factor. And we define T pi to be the Bellman operator of policy pi, where I guess everyone here knows its definition well, which is here. And we use Q pi to be the fixed point of T pi, and which is the Q function of policy pi. And J of pi is the expected discounted return of running policy pi, which equals to the value of Q pi at the initial state. So another important definition is the discounted state action occupancy, which is d pi. So d pi characterizes the state action visitation by the policy pi, which is here defined here. So in our paper, we are concerned with the offline setting, where we have a offline data D from the distribution mu. That is, the state action pairs are generated from the distribution mu, and the reward and next state follows the reward function and transition function. And also we have no coverage assumption on the offline data. So here is how we set up the problem. So what we have is very simple here. So we have an arbitrary offline data D from its distribution mu, and we also have a policy class pi and a function class f. So we use this function class f to estimate the Q function for the policies. The assumptions we rely on in our paper are standard. That is the realizability assumption and completeness assumption under any policy pi in our policies, which is I think pretty standard in the policy-based method. So the realizability assumption is basically saying that the true Q pi is approximately in our function class, and the completeness assumption basically is saying that the Bellman backup of any function in our function class is still approximately in our function class. And those two holds for any policy pi in our policy class. And the formal definition about how to define them approximately is here. So which is basically for the approximate realizability, we use the Bellman error of the best value function over any admissible distribution mu, and we assume that is bounded by some small constant epsilon f. And for the approximated completeness, we say that the function class f is approximately closed under Bellman operator T pi, where pi can be any policy, and note that we only measure that under the data distribution mu, which is here, which is relatively different than the realizability assumption.
Sorry, may I ask a question?
Sure, yeah.
About what does it mean to be admissible distribution in
I
your
see. Yeah.
definition?
So the admissible distribution I mean here is that nu can be any discounted stationary distribution of SA from any policy, which means like mu can be d pi of any pi. That is basically admissible here.
Okay, thanks.
Yeah. So since we don't have any coverage assumption on the offline data, so we may not hope to learn the optimal policy anymore. So what should be the desired guarantee in offline reinforcement learning? So actually, we may only hope to do well within our data coverage. So if we want to translate that in math, that is, when we have a single policy considerability for a arbitrary competitor policy pi, the performance of our learned policy pi hat can be lower bounded by the performance of the competitor policy of pi approximately, which means our learned policy pi hat shouldn't be worse than that competitor policy pi too much. So, and here, the single policy considerability is defined in this way, which measures the distribution shift between d pi and mu. And note that in this definition, we use f minus f prime to be the sort of like the test function, which makes it always tighter than the regular density ratio style definition. I may also want to emphasize that the classical battery reinforcement learning method usually need a uniform considerability coefficient, which measures the worst possible distribution shift over the whole policy class, which is basically here. They need to measure the best pi of all C pi, and whereas our method only depends on the coverage of single competitor policy. So any questions so far about the setup?
Yeah, can you explain a little bit more the definition of concentrability that you are using here as the ratio of the error? I mean, I would have expected to depend on the Bellman operator there, but I guess it's a little bit
Yes.
encompassed by the F prime, the
That's
difference
a
between
great
F and
question.
F prime.
Yes. So actually, the original definition of this like single policy considerability in our paper is basically like f minus t pi f, and pi can be some other pi. However, since we also use this like completeness assumption, which means like any t pi f is also roughly in our function class, so that this one is actually a upper bound of that one using the Bellman error, and which is more simple and intuitive, I think.
Okay, I see. And the fact that is approximate close that doesn't impact in any way the result, the definition of concentrability.
Yes. So yes here. If we don't have that, if we don't have this epsilon ff, then this one should be perfect. And if we have that, there should be a little bit different, but we want to use that to make our derivation to be simple enough. And in the formal theory, we may want to change this f prime to the like Bellman backup of this f. So this is only for the simple of our like intuition.
Okay,
Yeah.
Thanks.
I think someone else had their hand up. Do you still have a question?
I figured it out for myself. Thanks.
Okay, brilliant.
Yeah, thank you. So let me continue. So now let me tell you. About how could we achieve that like offline reinforcement learning guarantee, which should use our Bellman-consistent pessimism. So I should mention that our Bellman-consistent pessimism is a general framework of designing offline reinforcement learning algorithm, and I will mainly focus on its information theoretical property next, and after that I will tell you how to do that in practice. So let's first recall what is the goal of regular reinforcement learning. So that is, we want to find the optimal policy over the whole policy space, which has the largest discounted return, and the discounted return equals to its true Q function at the initial state. So in typical policy-based method, we may want to achieve that by evaluating the performance of each policy and pick the best one, right? However, having an accurate evaluation of all policy in the policy set is not always possible in the offline setting. That is because in the offline setting, the offline data may not have sufficient coverage for the state action that every policy would visit, which makes it very difficult to estimate the quality of all the policies only from our offline data. And informally, when the data distribution have a sufficient coverage over the policy's state action visitation, we will say this policy is covered by the offline data.
Sorry for interrupting again. I have a
Sure.
question about the notation. I
Yeah.
may have missed it, but the notation Q pi S 0 pi, what does denote?
Oh, I see. So that is basically like summation over A of Q I0 A times pi A given S. Roughly
Okay,
that.
okay. So it's the
Yeah.
expectation under the policy. And
Yes,
so
yes.
then a question associated to this is important to consider stochastic policy, or is just for generality, or is really important to get the best performance out there to have stochastic policies?
Yeah. So we don't need any assumption on the stochastic policy. On the deterministic policy, and any stochastic policy class still like works here. Yeah.
Okay, thanks.
Yeah. So now let me continue. So for example, in this figure, this large red area denotes the place that could be visited by some policy in the policy class, and we use this blue region to be the coverage of our data distribution mu. So in this case, we would say these policy pi1 and pi0 are covered by our offline data, and the optimal policy pi star is not covered by our offline data. And ideally, we cannot hope to find a good policy if the data coverage contains no good policy. For example, we cannot hope to learn this pi star in this case, but we can hope to compete with the best policy within our data coverage. Yeah. So how to do that? Here is our proposal. Although having an accurate evaluation of each policy in the policy set is not always possible, we can still do our best to have a pessimistic evaluation of each of them. Roughly speaking, the pessimistic evaluation means, given our offline data D and our function class F, what should be the worst possible performance of a given policy pi? So intuitively, we can have a relative accurate evaluation for the policies within the data coverage, so that the pessimistic evaluation should be close to their true performance. On the other hand, the policies outside this blue region should have a low pessimistic evaluation, because their performance is largely unknown to us only from the given offline data, and the worst possible case can be really bad. Therefore, these intuition could help us to pick the best policy within our data coverage. So, any questions so far about our concept?
Can I ask a question?
Sure.
Hi, this is Shipra. So you have this different measure of this constant concentrability instead of the
Yes.
ratio, but does that measure being less than infinity still imply the ratio is less than infinity? Do you still need there to be a non-zero coverage?
Non-zero coverage.
Yeah.
So
So
it
does
means
this?
that
Do
I
you
see.
still kind of assume it's less than infinity, even though your constant is different?
So
The ratio, yeah.
so your question is do we need to assume the ratio is less than infinity even though we use this test function based definition? Is that your question?
Yeah, I understand that the constant that appears in your bounds is different from the ratio.
Yes.
But does that constant being less than infinity still imply that the ratio is less than infinity?
I don't think so. So I don't.
Okay.
So I don't think so. For example, there are if there are two states or two state action pairs, their performance are very similar, and their value functions in our value function class are also very similar, And in this case, if we only have visitation for one state, but we can still use our function class to generalize the property of the other state, which means roughly speaking, in this case, the ratio can be infinity for this unknown state, but our concentrability definition can leverage the generalization from the function class and may not be infinity anymore. So is that answer your question?
Yeah,
you can
Shipra, I think
yeah.
Tengyan will we'll see a concrete extension later in the linear NTP setting where the linear structure really allows you to generalize across state action pairs. So there, like you can, I mean, in principle, you can even have a data set that provides good coverage by just having something like by just having data from these state action pairs, as long as their features are, relatively independent of each other. So this, in some cases, this can be a much tighter notion of coverage than the density ratio based one.
Okay, thank you.
Yeah, thank you, Shipra. Yeah. So let me continue. So based on now let me talk about the algorithm here. So based on that concept of picking up the policy with the best pessimistic evaluation, we can construct a version space f pi epsilon for every policy pi in the whole policy set. The insight of this version space is that since the true Q function always have 0 Bellman error pointwisely, we can choose some small epsilon such that this version space f pi epsilon contains all value functions that have small Bellman error. In this way, we can consider f pi epsilon to contain all the plausible Q functions of policy pi given the offline data D. And of course, the true Q function Q pi is also included in this version space. And therefore, if we use the most pessimistic function in this version space as our estimation of pi's performance, we know this one should be at least more pessimistic than its true value. So this is basically the Q pi path as I mentioned before. And finally, we can pick the best policy based on that pessimistic estimation. So note that this is an information theoretical algorithm, and I will talk about its practical variant later, which still enjoys theoretical guarantees. And one more thing I should remark is that since we usually don't have the access of the Bellman operator T pi, we can use this one to be its approximation, which is firstly introduced by Antosh et al. In 2008. So any question about that?
Yeah, I have maybe a very simple question.
Sure.
Is about the fact that is enough the characteristics that you ask about at the beginning. The assumption are all the approximated. So I guess by tuning epsilon, you can deal with the fact that the Bellman operator is approximately close and all this property, right? Everything will be in epsilon in the way of choosing epsilon, right?
Yeah. So I'm not sure I fully get your question. So you mean by tuning epsilon and using this one, we can still bound the Bellman error, is that?
Yeah, exactly. That was my question, in the sense that all the terms that you defined before, epsilon f and epsilon ff, are going to be used to define these terms epsilon that you are using here in defining the set.
Yes. So this epsilon should be related to both approximation error, epsilon ff, and epsilon f, and also the statistical error. And by tuning this epsilon based on these three value, and we can say that if this one is smaller or equal to some epsilon based on that three value, the Bellman error, the unsupported Bellman error of this f should be also smaller or equal to another small epsilon. We will have that.
Yeah, right. That was my question.
Yeah, thank you. So now let me talk about how our proposed approach works. So at first, let pi to be some arbitrary competitor policy, and our target is to bound j pi minus j pi hat, which is the performance difference between the competitor policy and our learned policy. So since the version space we construct contains all plausible value functions, we can use the most optimistic one in the version space to upper bound the performance of policy pi, and we can use the most pessimistic one to lower bound the performance of policy pi hat. And also, I should remark that different policies typically have different version space. And as you can see here, the max is over the version space of policy pi, and the mean is mean over the version space of policy pi hat. Yeah. So next, due to the optimality of pi hat, which means pi hat has the largest pessimistic estimation, we can then use the pessimistic evaluation of pi to lower bound the pessimistic evaluation of pi hat, which is basically like we change the pi hat to be pi here because of we have this guarantee. And we define these f pi max and f pi mean to denote the corresponding optimistic and pessimistic value functions for policy pi. We will use that later, yeah, for simplicity.
Sorry,
And,
a quick
sure.
question here, just for my understanding. Pi and pi hat are in some way related to the basically space that is covered by your data, or can be any policy? Because I'm
so
thinking,
pi and what? Can you repeat that again?
Yeah, it's, at the beginning you discussed the fact that certain policy may be estimated by the data that you have because are covered by are well approximated under the sampling distribution. I'm wondering if here, when you're talking about pi and pi hat, is there some connection with how good are the data for estimating one another? Since you're using an upper bound and the lower bound for the two term, I'm wondering if you can say this for any possible policy, or implicitly you are using some connection with the data that you are generating. And this is my guess, but I'm not sure to understand where is entering this aspect.
Let me try to digest your question. So, so you mean like since the construction of version space, like of this since the construction of these two version spaces are similar because we all use the unsupported Bellman error, is there any connection between them or not? Is that your question?
No,
I think the confusion might be that is this true? Are these statements true for all epsilon and all pi, or is epsilon and pi somehow connected through that assumption?
Yeah, exactly.
I see. Let me see.
Because just to clarify, my doubt is that all the properties that you defined are with respect, in one case with respect to the admissible distribution, in the other case with respect to the sampling distribution mu. So I'm wondering if here in the derivation that you're doing, if policy and epsilon are related in some way, basically
I see. So I think the epsilon here, the statistical error contains which is from the union bound from all the policy class and function class. That is how we get that epsilon before. So which means that epsilon depends on the cardinality of the policy class, and which makes that holds uniformly for the all policy in our policy class. So that is the intuition. So is that a good answer?
I think part of the question, if I get it correctly, is I think Matteo is asking, do we need this comparator policy pi to be covered by the data, right?
Oh, I see.
So
I see.
At least so far in this derivation, and also in our guarantee, we don't really make any such assumption for pi. So this is a more general, robust guarantee.
No. So in our information theoretical result, we may need this pi to be in our policy class.
Because, no. You're not getting what I'm saying. Yes, we need it to be in our class, but we don't need it to be covered, right? We're competing with an arbitrary policy in our class. But as we will see, this upper bound, you will pay a term that is related to kind of like the escaping probability. That is how much mass you put outside the data distribution. So if you compete with a policy that is that is not covered, the guarantee can be relatively vacuous. But the guarantee will be tight if you compare to a policy that is well covered.
Yes.
Okay, got it. Was exactly that my question. Thanks, Nan.
Yeah, thank you, Nan. Thank you, Matteo. Thank you, Shiver. Yeah. So now let me continue. So by using some standard telescoping argument, we can further bound these by using their Bellman error over the distribution of d pi. So the way for doing so is just like minus and plus the true j of pi between this max and mean. And then we can use some like very standard we can use some very standard telescoping argument like to bound like this like f pi mean minus the j of pi, and we can get this. So next, since we know like both f pi max and f pi mean are chosen from the version space, and any value function in the version space should have a small Bellman error over the data distribution due to the Bellman error constraint of the version space. We can use that fact to split the Bellman error over d pi to two parts, the unsupported part and off-support part, and bound them separately. For example, we can choose some unsupported distribution nu that pay the distribution shift effect between this unsupported distribution nu and data distribution mu, and this distribution shift effect is basically the single policy considerability as we mentioned before. And for the off-support part, we need to consider the amount of off-support mass, as well as how bad we do over the off-support mass. And the off-support mass is basically controlled by this like density-related function d pi minus nu, where we remove the unsupported distribution nu from the distribution of d pi, which is formally defined here. Oh, and I should say that these expectation like d pi minus mu is a little bit abused here, because d pi minus nu is not actually a density function, but I mean the calculation of that is very similar to the density. That's why we use that. And it is also interesting that this unsupported and off-support splitting can be viewed as another form of bias variance trade-off, and I will talk about that later. So this is mainly about how our method works.
Sorry, just a quick question.
Sure.
So this new here, is this at the moment it's just an arbitrary distribution and you're going to optimize over it later?
Yes. So this new can be arbitrary unsupported distribution, and our bound will follow the best choice of new.
Okay, thanks.
Yeah.
So basically, it's still in this direction. Since the second term, if I'm not misled, you can always put it to 0 because nu is an admissible distribution, so d pi is in that. There is no trivial solution that basically by setting nu equal to the stationary distribution of pi, the first will be the minimizer of this.
Right. So so actually our bound also includes like the mean of nu, and we don't have a like explicit solution like which nu is the best.
Okay.
Yeah. So basically, like the bound hold, this nu is only a analysis device, right? So you can just choose arbitrarily. And I guess, Matteo, you're asking a case where, for example, some comparative policy pi is actually covered by data. So in this case, you can always just choose nu to be d pi itself, right? And then d pi / nu, which would be 0. So that's a valid bound, but who knows, like there may be other way of splitting in specific case that gives you better guarantee. But we don't know how much better you can get without more detailed information about the specific case.
Okay, got it. Thanks.
Yeah, thank you. So now let's go to our detailed theoretical guarantee. So to make it cleaner, I will ignore all the approximation error which can be characterized in some pretty standard way. As we mentioned before, our result includes both on-support part and off-support part, which is determined by the on-support distribution nu, which we can choose any on-support distribution. And the unsupported part here is actually same as what we desired, which is the distribution shift effect times the very standard error term from the concentration. And now this C, which is the single policy considerability of nu, measures the distribution shift effect.
Can I ask one question?
Sure.
So in the algorithm, it's simply choosing that pessimistic policy from this region F by epsilon, right?
Yes.
What is epsilon there?
Oh.
Does it use this C, or like what's the is there an expression for it?
Yes, thank you for the great question. So epsilon is basically depends on the error from concentration and the approximation error. So basically the intuition of epsilon is that if we measure the unsupport Bellman error of the true Q pi, what should be the value of that? And we basically only need to set the epsilon to be that value of true Q pi because what we only need is to guarantee the true Q pi is in our version space, and that's all. Yeah, so that is how we choose epsilon. And after that, we can see epsilon is basically the combination of epsilon f, and the very standard statistic error. And I mean, no C dependency in the epsilon. Yeah.
Okay, thank you.
Yeah, thank you. So now let's go to our off-support part. So the off-support part depends on our remaining density, which removes the on-support density nu from d pi, as we mentioned before. And we define delta f pi to be here, which used to measure how bad we do in the off-support region. Roughly speaking, if f pi max is mostly agree with the f pi mean, which means we did well in the off-support region, and otherwise it means we did bad in the we did poorly in the off-support region. And I should remark that the competitor policy pi, the on-support distribution nu, and the constant C can be chosen arbitrarily, and our bound adapts to the best choice of them. Yeah. So another interesting thing is that the on-support off-support sublithium can be viewed as a bias variance trade-off. That is, some sublithium could have small off-support mass, but it needs to pay some large distribution shift effect. On the other hand, some other sublithium needs to pay a little bit more on the off-support mass. However, we can reduce the distribution shift effects a lot, as you can see. If we use the on-support off-support sublithium here, the C should be large, but we have very little off-support mass. On the other hand, if we use C here, the C can be relative smaller, but we have like relative larger off support mass. And as we mentioned before, I mean as we mentioned before, our theoretical guarantee can automatically achieve the like bias variance trade-off. So any questions so far about the guarantee? Yeah, great. So here is a comparison between the different pessimism framework. So currently there are mainly 2 lines of work, and the use of the principle of that use the principle of pessimism to solve offline reinforcement learning. The first one is the pointwise pessimism. That is, we estimate a Q function that has a lower value than the true Q pi for every state action pair, and most of the existing work of offline reinforcement learning follows on this line. And our paper is built on the Bellman-consistent pessimism, where we only care if we have a pessimistic evaluation of policy pi's performance, which equals to the Q function at the initial state at 0. And this means we only need to be pessimistic at S0, and for the following state, they will be controlled by the Bellman consistency. And in other words, this means the Bellman consistency will propagate the pessimism over the trajectory.
So maybe a question here. It reminds me a little bit also what is used for exploration in terms of optimism at the initial state or optimism at the state. So even here there is the usual challenge of being computationally efficient versus being efficient in statistically efficient.
Yeah, so currently in this information theoretical result, it is not computationally efficient, but I will tell you like how to do a computationally tractable way next. Yeah.
Okay, great, thanks.
Yeah. So now let me talk about some advantages about our like Bellman consistent framework. So the most important one is our Bellman consistent pessimism only needs weaker expressivity assumption than the pointwise one, so that it could be applied to any function approximator by using some standard assumption. The main insight behind that is, for any function class, there must be one function within them that has the lowest value on the initial state, and that is why the Bellman consistent pessimism can be applied to any function class. However, choosing a function that is pessimistic pointwisely usually needs some more stronger assumptions. For example, in linear MDP, case, we only need to use the linear function, whereas the pointwise pessimism also need a negative quadratic bonus to achieve that. So here is the result about using our method in linear function approximation. So in this case, our function class is linear, and the algorithm is similar as before. And I should remark that in this case, we can just use here the mean squared projected Bellman error MSPBE to construct our version space, which has the same solution of that like minimax one as we mentioned before, which is also showed by Antouche et al. Yeah. So here is here in the bound, this sigma d term is the covariance matrix, and this large expectation term can be viewed as a single policy considerability in the linear case. And yet this term is almost same as almost same as the existing work, so we can have a like pretty direct comparison with them. And compared with Jing et al., who use like the bonus-based pessimism, we can save a linear in D term. That is because we only use the linear function class, whereas they also use a negative quadratic term. We also remark that our method also need to induce a additional log A term compared with their work. However, that can be further resolved by the concurrent work, the Nate et al., which also using the same intuition of being pessimism as the initial state, and their work focuses more on the linear case. So that's all for the information theoretical algorithms. So any questions so far?
Yeah, exactly. I mean, Nan already answered my question on the chat. Should be a square root of the improvement, if I understood correctly, not a D, right?
Yeah, so it's D to square root D, right? So the saving is square root D, not D, because
right.
D squared to D is
yes,
inside the square root.
Sorry about that. Yes.
Yeah.
And the second question I had is to better understanding this bound, because your previous bound was depending on C that was optimized through the distribution nu. So here there is no dependence on
I see.
nu, so you
yeah.
optimize directly the bound using a specific distribution, and then what is this distribution? What is the best choice then?
I see. So in this case, actually, in this case, that's equal to like we take nu to be d pi. So where we now only have on-support part and no off-support part anymore. And I should say that there might be some better choice of C, but we just want to make it, I mean, as clean as possible as here.
Okay, got it. So this is related to my previous question, where setting d pi was good, was optimal or not. Okay. Thanks.
Yeah, I think the role of the splitting is more sort of, in those subtle cases. For example, you have a policy pi you want to compete with, and it's almost covered by your data, but it's just have a little bit of mass left, right? So our result, the most general result, allow you to just cut it off. Whereas if like these kind of results, which set nu equals d pi, you just can't compete with those policies like altogether. So our results give you more flexibility in those cases. And in this case, we just choose nu equals d pi because this allows us to directly compare to existing results, which usually don't do this splitting at all.
Okay, thanks. So then maybe another question. I can set pi to be pi star, right? And the same reasoning we rolled, right? It's for any pi there.
Yes.
Okay, good.
Yeah, so let me tell about like how to do that in a computationally tractable way. Yeah.
Can I ask something about the theory?
Sure.
Quickly, last question. So the improvement, is it like just some insight? Like, is it mainly because of the difference in the two concentration? So if I had the coverage in the traditional sense, in this setting, will the difference be d versus square like d squared for the coverage number, that ratio that you define versus the upper bound that is usually used, or is the difference due to a different algorithm? Like, where is the
I see.
main improvement?
I think that difference is due to the actual value function we use, because in the bonus based method we also need to use a quadratic bonus plus the value function, linear value function minus a quadratic bonus, which make our function class to be actually quadratic function. And here our method is only use a linear function class. So so that is mainly the source of d square and d. Yeah.
Thank you.
Yeah, thank you. So let me talk about how to do that in a computationally efficient way. Yeah. So actually, there are two main bottlenecks about using our information theoretical algorithm in practice. The first one is how to do the policy optimization here. With over is pessimistic policy pessimistic policy evaluation. That is hard because the version space for all the policy are actually different, and yeah. And the second one is how to find the most pessimistic policy evaluation over the version space in practice, especially given we may not want to construct the version space explicitly. And here are our solutions. For the policy optimization part, we can just use the mirror descent update. That is, for every step, we do the pessimistic estimation for the current policy, which is here, and then we use the exponential update based on those pessimistic estimations. And the output policy should be the uniform mixture over all historical policy at the trajectory level. And it is interesting that although the policy obtained in this way may not be same as the true argmax solution, which is the information theoretical result, it could still achieve a similar performance guarantee as we showed before. And also, I may need to mention that the policy class we use here is actually different from the information theoretical one because of that exponential update. Okay. Yeah. So now let's look at the pessimistic policy evaluation part. So we have shown that by changing the constraint to regularization and choosing some lambda properly according to the value of epsilon, these regularized optimization problem could still perform enough pessimism as we want. So here is the theoretical guarantee of our practical algorithm, and also I will ignore all the approximation error due to the purpose of simplicity. So now we can decompose our bound to three terms: on-support error, off-support error, and optimization error. The optimization error term is very standard from the online learning papers, and I will focus more on the on-support part and off-support part next. So let's first talk about the on-support part, which is here. So compared with the information theoretical algorithm, we can notice there are two main drawbacks from this practical variant. The first one is the statistical rate is actually slower than the information theoretical one, which is here. That is because we use the regularized pessimistic evaluation rather than the constrained one. Another thing is that we need to introduce another T term because of the policy class complexity, where the policy class is here a mixture of T of value functions. And I think addressing those two issues is the most interesting future directions of our work. So now let's look at the off-support part, which is here. And since there is no explicit version space anymore, it now only depends on the Bellman error of the FT, which is the pessimistic value function we get from our algorithm. And the other things are almost the same as the information theoretical one. So any questions so far about this practical variant?
No, it's
Okay.
that there is no question.
So yeah, another thing I should remark that our practical algorithm is actually fully computationally efficient in linear case, which is just solving a quadratic problem. So how to do that? How to show that? So at first, as we mentioned, we can change the Bellman error to be this estimator, And after that, since the solution of mean squared Bellman error is same as this one, we can then change this one to be the MSPBE. And after that, we have showed in our paper that this pessimistic policy evaluation objective is actually a quadratic form of theta, where theta is the only parameter of our linear class. So that's why our algorithm is fully computationally efficient in the linear case. Okay, so now let me summarize my talk. So here are some related works about offline reinforced learning. So on the theoretical side, Liu et al. Proposed an approach about general function with general function approximation plus some relative stronger assumptions. Jing et al. And the Nate et al. Studies offline reinforced learning in different linear cases. Also, Masatoshi et al. Proposed a model-based approach and just presented in the same seminar several weeks ago. And on empirical side, there are also lots of papers about like both model-based and model-free offline reinforcement learning, but their paper usually built upon a tabular theory. So our paper proposed a general framework of offline reinforcement learning that apply to general function approximation. It is simple but probably efficient under standard assumption. And we also provide an implementing friendly practical algorithm, which is even fully computationally tractable in the linear case. And there are some interesting future directions. The first one is how to provide a computationally efficient algorithm with this like good rate, correct rate. And I think the key difficulty here is the complexity of our policy class, because in this case, the complexity of our policy class may depend exponentially on that of our value function class, which will give us a bad rate from the like uniform convergence. Another thing is that how to make it more scalable in large-scale scenario, which is our current ongoing work. And the last one is how to tune the hyperparameter fully offline. So the reason for that is currently the workflow for offline reinforcement learning is that we may need to use online to evaluate the performance of each hyperparameter and choose the best one from them. So how to do that fully offline is still unknown. So yeah, that's all of my talk. Thank you so much.
Thanks a lot for the interesting talk. We have time for question. As Kira mentioned, if you have any question, you can type it in the chat or directly ask it at this point. So I have a question that is a little bit hinting on what is the best performance we can get, in the sense that what is in certain sense the lower bound or the property that makes the best thing we can achieve in offline setting, particularly on the quality, on the distribution, mu from where you're sampling from, and so on and so forth, just to understand how far we are, or if you're already matching correctly the rate. There is any information there about this sort of lower bound in this setting?
I see. So actually, we have I have another paper provides a tabular offline lower bound, which is roughly saying that. Let me go to the information theoretical result, which is roughly saying that. Let me see where I should use. Let me use this one. Yeah. So if we have single policy concentrability of pi star, then our lower bound has to depend on the on the square root of C star, where C star is the single policy considerability of pi star. So which means I think the dependency of C is almost the best we can achieve here. And in terms of H, I think there might be possible to improve one H here, because like V max contains an H, and and 1 minus gamma contains an H, so that is basically H. That is basically H to the power of 2, and however in our tabular theory, I think we can finally achieve H to the power of 1.5, which could save another square root of H. So there possibly another room for improvement.
Okay, thanks for the clarification. I was wondering also a little bit in terms of, if you want a more problem-dependent view on what you can do, because if I remember correctly, your result in the linear case, so depends in a certain sense on how well defined is the covariance matrix, so the inverse of the design matrix, given your data. And I was wondering whether if your sample cover all the direction, what you can get in terms of better results there that are a little bit more problem dependent, of course, because it depends on the type of data, but whether there are specific cases in which we can do better, just because it's maybe simpler and you are covering the entire possible space.
I see. So your question is how can we get a sort of the instancy optimal style result?
Well, before that, I think the thing here is that in this result, by using sigma d inverse, you think it's implicitly assuming that sigma d is full rank, right? But it actually doesn't have to be the case. For example, if sigma d only covers a few directions and does not cover other directions, but phi SA under d pi never hit those directions, you can basically generalize the result and still have this quantity is still bounded, right? And furthermore, because of our previous splitting, if you rarely hit phi SA outside the subspace spanned by D, you can just do that bias variance, that splitting, and split off those. So I mean, this result here is simplified to, and we remove these details, but we can certainly handle the case where D is sigma D is not full rank.
Okay, got it. Thanks. I missed that aspect.
Thank you.
Any question from people? Yeah.
Just so you've shown these results here, which are for your errors being 0, these epsilons being 0. What sort of effect do they have when they're not 0?
So you mean if epsilon is not 0, what should be the bound look like?
Yeah. Just a feel for what changes.
In the information theoretical result, there will be another term that's roughly like C times the square root of the summation of those two stuff. And in the practical one, the rate should be worse, which should be like this term should plus a epsilon f and epsilon ff inside these
Sorry, which term do you mean?
I mean in the unsupported part term, this guy will also plus epsilon f and epsilon ff inside this. So which means in our current practical result, the bound depends worse on the approximation error than the information theoretical one.
Yeah, I mean, in general, in these analyses, what happens is that you need to handle the statistical error anyway, right? And when you have approximation error, usually they just add pretty straightforwardly additively into your analysis. So whatever dependence you have on this, 1 over square root 1 over n term, usually you just add to that the approximation error and multiply basically the same factors, and the results are really the results for the approximate case is not that different.
That makes sense. Thanks. Matteo, I think you're muted.
sorry. I just realized that at some point you mentioned that your algorithm, the mirror descent type of algorithm, is efficient. I was just wondering, I may missed it, but efficient in the sense that you can solve it in closed form, the optimization step, or is something that is simply, some sort of a quadratic? Because I remember you mentioned quadratic problem, but I don't know if they emit a closed form solution in that sense or not.
I see. Sorry about the confusion. So what I mean is basically like these pessimistic policy evaluation step can be solved by some LSTD style closed form solution.
Okay.
And then since the like exponential update is pretty straightforward, which is also like closed form here, yeah, that's why I mentioned like that it's like fully computationally retractable. And also and also one more thing I may also want to mention is that I think the LSTD style closed form solution need to assume that the covariance matrix is full rank because of also this like projection operator needs. And if we don't have that, I'm not sure if the like LSTD style closed form solution is if the LSTD style closed form solution still hold. However, we will always have this quadratic form no matter if we have or not this like full rank assumption, which means like these objective will be always like computationally efficient because that is a quadratic form, right?
Yeah. So in general, when you have like rank deficiency, these quadratic objectives can, I guess, behave badly in some directions. But I guess in general, you can also incorporate additional norm constraint on theta, right? So in general, this pessimistic policy evaluation step asks you to solve a quadratic objective in theta with PSD Hessian, maybe in addition to some additional norm constraints. That's all you need to do in a linear case. And once you solve that, you just plug the learned linear function into the mirror descent update. So that's why we think like this overall is computationally efficient.
Okay, got it. Thanks.